Okay, now we're moving from experiments to assessing association. So you recall that to prove that one variable causes a change in another, the first criterion we have to meet is association. So let's look at association first. It's important to remember that just because we show that two variables are associated, that does not alone mean that one causes change in the other. We have two more criteria we need to meet. But assessing association is the very first step we need to meet. So I've already defined association. Two variables are associated when they change together or they exist or co-occur together. We have two types of association. We've already discussed this previously in the semester. I'm just putting it here for completeness' sake. Positive association is when both variables are moving in the same direction. Either both are going up or both are going down. And negative association means one is going up and one is going down. Okay, so two types of association. The simplest way to assess association is to make what we call a contingency table, also known as a cross-tabulation or a crosstab for short. So I'm going to show you how to make one using the SDA software. So open up a web browser if you have one, and follow along with me if you can. So go to a Google, search for SDA Archive. SDA Archive. And this is the link we're looking for here. I think if you type in archives, SDA Archives, you're going to get Seventh-day Adventists. We don't want that. We want archive-SDA. So I'm going to click on that first link there. And I'm going to scroll down, and I'm going to choose the General Social Survey, the very first one, 1972 to 2018. Pretty soon, 2020 will be available. For right now, I've got 2018 is the latest one. And let's just look for a couple of variables to Okay, so my example here is the relationship between your sex and your political party identification. I want to know if men and women have different preferences in political parties. So my independent variable here is sex. I think perhaps your sex causes women to be more likely to align with Democrats and men more likely to align with Republicans. So my independent variable is sex, and the sex goes in the column. So I'm going to type sex in the column box over here, and I'm going to type party ID. Party ID is the name of the variable that measures your political party preference. Party ID goes in rows. So set it up like this: sex in the column box, party ID in the rows. And then click the Run the Table button here. I'm out in the backyard, a little too far from the router, so it's going slow for me. And there's the table. Now, what we're looking at in this particular table are these bolded numbers. These are the percentages. And the way we read this table is we compare the bolded numbers across the rows. We're interested in the colored rows here. Don't worry about the color. That's beyond the scope of this course right now. But those, just know that the colored cells are the ones that we're looking at. So when I want to compare men and women, I want to compare categories of my independent variable. Sex is my independent variable. The categories of the independent variable are male and female. I'm comparing men and women. I want to know if there's a difference between men and women when it comes to party ID. So I'm comparing these percentages across the rows. So men are 14%. 14% of men said they were strong Democrats. 16.3% of women said they were strong Democrats. So women are a little bit more likely to say that they're strong Democrats, 2 percentage points more likely. Let's look at Republicans. Men are a little bit more likely than women to say they're strong Republicans. 10.8% of men are strong Republicans, 9.3% of women are strong Republicans. So this is the first step in using a table to assess association and to begin to test our hypothesis. And there does seem to be a small association. Note that the differences between men and women, when we compare these percentages across rows, the differences are not much. About 2% in this row, about 4% in this row, only 0.5% in that row, 2%, less than 1%. Yeah, less than 1%. So if we compare each of these rows, there's very little difference between men and women. The biggest one is this one here, where it's a little bit more than 4%. These are Democrats, but not strong Democrats, and more women are not strong Democrats than men. Okay, so that is an example of a contingency table, also known as a cross-tabulation or crosstab. It's a table with two variables. And here are my rules. If we have a causal hypothesis, then the convention is to put the independent variable in the columns and the dependent variable in the rows. So you can see that I put sex is my independent variable that goes in the columns. The column headers are for sex. The dependent variable is party ID that goes in the rows. That's rule 1. That's just a convention. It's like driving on the right-hand side of the road. You could do it the other way, but it's going to cause you trouble if you do it the other way. So do it the way everybody else does it. Rule number 2, when reading a table that's constructed according to rule 1, we compare percentages across the rows. That's how we read the table. We compare categories of the independent variable, percentages across rows. Basically, we're comparing men and women. Do women have a higher percentage of strong Democrats than men? Yes, they do, by a little bit. Measuring the strength of an association. Now, you saw what I did. I looked at the difference between men and women. In this row, strong Democrat, it's 2.2%. In other words, 16.3 is 2.2% more than 14.1. I just subtract the lowest one from the highest one. There's a 2.2% difference. And there's a word for that. It's called delta. Delta is a Greek letter, D. It's equivalent to D in English. D for difference, or delta for difference. I'm looking at the difference between men and women. The difference is about 2.2% in this row, the strong Democrat row. So we use delta to measure the strength of an association between two variables. And I can see in this table, the strength is not great. It's only about 2 percentage points difference. Ranges from, if we compare the deltas of the different rows, each row has its own delta. As we take the difference between men and women in each row, this one it's only 0.6%, this one it's about 4%. So the delta ranges from about 0.5% to about 4%. That's not very much. There's not very much difference between men and women. The association between the two variables is weak. It's only about 4%. My own rule of thumb for interpreting delta, I like to see about 10% difference before I assume that it's really meaningful. If there's less than 10%, usually it's not meaningful. Now, there are exceptions to that. If I'm looking at something that's very rare, such as have you ever witnessed a shooting? Most people have not witnessed a shooting. But so if I see a table where 1% of men have witnessed a shooting and only 0.5% of women have witnessed a shooting, that's a very small delta, 0.5%. But I'm measuring something very rare. Another way of looking at it is to say that men are twice as likely as women to witness a shooting, 1% versus 0.5%, twice as much. So two different angles on the same thing. One person could say it's only 0.5%. That's trivial. That means nothing. Another person come along and say 1% versus 0.5%. That's twice as much. That's a lot. So interpreting statistics is sometimes as much an art as it is a craft or a science. My own personal rules, I usually like to see at least 10% before I assume that it's a meaningful difference, except in those circumstances where I'm looking at very rare things like witnessing a shooting. Some other test statistics that can be used to assess how strong the association is between two variables are gamma, phi, and Kramer's V. I'm putting these in here for completeness sake. If you've taken statistics, hopefully you learned how to use these. If not, maybe you can use these if you have a term paper and you need them. But these are some of the basic statistics that we use to assess the strength of an association between two variables in a table, in a crosstab. Gamma is another one. So you can read through those on your own. let's move to this last topic, which is statistical significance, SS for short. Statistical significance is a test of whether the relationship between two variables is meaningful or it's due to randomness. Statistical significance is expressed as a p-value. P stands for probability. It ranges between 0 and 1. So another way of saying that is it ranges between 0% and 100%. So we can interpret this as the odds that our table association was produced by random chance. The standard for social science is a p-value of less than 0.05. In other words, we want to be at least 95% certain. 0.05 means there's a 5% chance that your table was produced just by random variation. That little difference between men and women is just due to random variation. If we produced another table with a different sample, we might get something completely different. So we're looking for a p less than 0.05. We want to be 95% or more than 95% confident that our table results are not due to random chance. So this condition of having a p-value of less than 0.05 is called being statistically significant. And it's important to remember that being statistically significant does not necessarily mean that the effect of your independent variable on your dependent variable is large. It just means it's non-random. So this is sometimes a little bit confusing to students because the word significant, to most of us, it means something that's important or big or major. But in this particular case, statistically significant doesn't mean big or important or major. It just means non-random. So you could have a very small difference that is statistically significant. This difference between men and women, it might be statistically significant, but it's still small. Statistically significant just means that 2% difference there is not due to randomness. It's a real thing. So I'm not going to show you how to measure P. That's for your statistics teacher to do. I'm just trying to relate this to your statistics class. If you have not had statistics, then just remember what statistically significant means. It means a test of whether or not our findings are due to random chance or not due to random chance.